My name is Robert Owen. I'm the University Program Manager of Imagination Technologies, and it's our pleasure to welcome you to this MIPSfpga workshop. I'm very pleased that we have two of our most expert trainers here today, and I want you to keep them on their toes and ask whatever questions you want. No question is too difficult or too easy. I'd like to introduce Professor Daniel Chava Martinez. He's from University Complutense in Madrid. We've been working with Danny now for more than 2 years. He teaches this stuff with his students, so he knows how it works in the classroom. And with him is one of our experts from a development centre in Leeds in the UK. Zubair Kakakel is an expert on hardware and software and how the two interact. He's the guy that wrote the System on Chip package, which some of you may have downloaded and looked at, which shows you how to run Linux on MIPSfpga, and he will give you an overview of that today. So there are trainers, Zubair and Danny. Any questions you have about the university program, you're welcome to come to me. A very warm welcome to you. Thank you very much for being here today. I hope you have a really great day.
Thank you, Robert. Okay, so I don't need to do the introductions because they're already done. So this is a rough outline of how we'll conduct the workshop. There's parts 1 and 2 before the coffee break at 10:30, and then there's like parts 2, 3, we break for lunch, and we break for like the tea break. So it's pretty relaxed, but the sessions in the middle will be pretty intense. So the one thing that I can request you all is to just please make sure you come back at 11, please make sure you come back at 1:30, and please make sure you come back at 3, so that we can all start and keep the workshop on schedule. Thank you. So basically, what is MIPSfpga? MIPSfpga is an unobfuscated soft core. So basically, we took Imagination sells the MIPS microactive core, and we took the MIPS microactive core, the one we sold to Microchip, the one that went into the PIC32. We basically put it under an academic license, so universities can use it as is to teach MIPS to their students, and it comes with many other labs and exercises. There are 3 packages. The MIPSfpga Getting Started Guide, that's what just tries to talk about the interfaces, how the IP core can be brought up, the clock, reset power, and various interfaces around it. Then we have MIPSfpga Labs. These are a set of 25 labs which increase in complexity as you go. So it starts off with very basic, how to load stuff onto, load the bit stream on the Nexus 4 DDR board, how to compile some code and load it using the JTAG debugger. And then it moves on to the 7 segment, then it moves on to the interrupts, then it moves on to instruction flow inside the core itself, and cache controller, MMU, all sorts of like more complicated stuff. The 25 labs, they just increase in complexity. There's also a lab on user-defined instructions if you want to define your own instruction and see how that works. So the third package is MIPSfpga SoC. Now, this doesn't go inside the core, but all the things around it. So how do you use a MIPS core in the industry, use other IP cores to build an SoC around it, and the SoC, how do you build an SoC which is capable of running Linux at the end, and how do you then port Linux onto your new hardware platform on FPGA, and how do you build embedded Linux on top of it? So that's the third part in terms of SoC, so how can you run Linux on MIPSfpga. Now, I should have spoken all that here. Oops. Where did it go? Sorry. Which one's back? Okay, yeah. So yeah, that's the detail. Yeah. So you should all have received a flash drive on which there's the workshop materials. Does everybody have it? Copied all over? Okay, that's good. Now, the next thing is OpenOCD and Codescape toolchain. Has everybody already installed it? That's very good. No? Okay, so in the flash drive, there was one. If you want, can you just assist and start running it? It'll just help as we move forward. You can listen, and then you will assist and just start running it, okay? Thank you. Yeah, this just helps with timing later on. Okay, we'll be using this folder for all our labs and exercises during the workshop. It has all the bit streams, it has the code that we'll use, so just keep it in a handy place. And try and make sure there's no white space in the path, like a space in the path or anything. Okay, so Robert Owen, he's the head of Imagination University program. He spearheaded this entire teaching package, and it's been about 2 to 3 years to bring this all together. So there's a lot of work done by a lot of people, and he's been at the head of it all. Okay, so before we dive right in, we're gonna look at the history a bit, some topics and the background, and then we'll go inside the core itself, right? So the topic, so MIPSfpga Labs, the variety of things it covers is quite daunting. So you have the SoC design part, you have how assembly language C programming, how assembly bootstraps and enters C program, you can go up, all the way up to there. You have the instruction set architecture, of course, is the MIPS architecture and how that builds up. You can also teach Verilog and how Verilog is used in the industry and IP codes, instantiations, all sorts of things. Computer architecture, memory systems, memory mapped I/O and peripherals. This is also very all over, all the labs cover this. Interrupts and performance counters. So there's a lot of things that MIPSfpga covers over the topics that it covers over time. So the labs, they're sectioned into 4 parts. Okay, so parts 1, the introduction, the first 4 labs. It basically, how do you bring up the MIPS core on FPGA? How do you compile some code? How do you load code on to the FPGA through the bus blaster debugger or something? The second part, input output, so it deals more with the I/O on the Nexus 4 DDR board, the 7 segment, GPIOs, LEDs, stuff like that, how to I/O. Then the third part, that's the most intensive one. It goes inside the core. You see how instructions flow through the pipeline, stuff like that. User-defined instructions, extra features and stuff. And the memory subsystem as well. Scratchpad RAM, how do you use it, stuff like that. So as I mentioned earlier, the labs, the complexity increases as you go forward. Okay, so here's a breakdown of all the labs in it. The bold ones are the ones that we will be covering today. Okay, Vivado project, just loading the bitstream, C programming, how to load the code onto the FPGA core. We'll cover interrupts and how interrupts are handled on MIPS. We'll cover performance counters, and then we'll cover instruction flow, add. We'll cover some hazard logic, or extend basic caching and cache structure over the course as we go forward. All right. So before we step in, a bit of history for those not familiar with the MIPS architecture. So it was designed in the 1980s in Stanford by John Hennessy. He wrote the famous book Patterson and Hennessy as well. It was one of the first RISC architectures, and Hennessy himself co-founded MIPS Computer Systems, which was then MIPS Technologies. It's used in many commercial places, Nintendo machines, Cisco servers. There's many, it's studied in a lot of universities. There's many books written about the MIPS architecture. Imagination Technologies, we purchased MIPS Technologies in 2013. That's why there's an Imagination logo next to MIPS. So MIPS was independent, but Imagination then purchased it in February 2013. Imagination, we also have other IP products like Power VR and Sigma IP products and stuff like that. But for today's workshop is about MIPSfpga. So MIPS cores come in many flavors. As you know, you have cores that go into microwaves, cores that go into desktop servers, cores that go into your Wi-Fi router. So there are 3 classes. We call them M, I, and P class. So M is the micro, small kind of microcontroller type category. I is the intermediate category. Lots of your Wi-Fi routers have the I class. P is the performance class. Now, MIPSfpga, the core itself, is the M class core, but it can still go up to like 300-400 megahertz clock speed, and it can run Linux. It also has the MMU, so don't be confused that it's a very small microcontroller. It can be configured to be a microcontroller or a microprocessor to run Linux with an MMU or just a microcontroller. So MIPSfpga itself, the code we give, is the microactive. Okay, so more about MIPSfpga. It's a commercial soft core implemented on an FPGA platform, made available to universities by Imagination Technologies. You can see the whole source code. There's no hidden parts in it. You just open up the pipeline, open it, the Verilog files are open. If you want to open the cache, files are open. The MMU, the files are open. And of course, the ALU and the instruction decoder as well. Okay, so but it's specifically for universities. The terms are simple, academic use. Faculty members are requested that each of them should register individually so that we can keep a bit of track. You can't put it into Silicon as is, but we do have a track with Euro practice where you can license and go with Silicon production if you want. Okay. Any publications you're free to publish, but it's just you should acknowledge that the work was done on the MIPSfpga platform. And we'd very much appreciate if you can send copies of your journal publications. Even if they're not published, just drafts would be good, because we've received many drafts. Some people have published just multiple instances. I think it was 500 instances of MIPSfpga on a big FPGA and try to make them communicate among each other to be a multi-cluster kind of environment. So we have received quite very interesting journal papers, and some of them have been published as well. Okay, so just to recap, it's a 5-stage pipeline in the microactive core, 1.5 dry stone MIPS per megahertz in terms of performance. We have a 2-way instruction and data caches, 2 kilobytes each, and we do have a memory management unit and a DLP as well. There are some labs that go over the DLP caches and all sorts of things. Okay, so this is a diagram from the data sheet itself about the MIPS core. It can look complicated, but most of it, like each one by one, they're covered in the labs, and we will cover some of them in depth, hands-on here today. Just for the start, the parts that we are really concerned about is these sections, the general purpose registers. Okay, we store scratch RAM, just variables in and out here. The multiply and divide unit and the ALU instruction decoder. This is the section that covers those. We're also going to use the JTAG interface. So MIPS cores come with an EJTAG interface. These are the wires that basically plug into the bus blaster or the debugger, and that's how we load program code onto the memory. And the third thing is the AHB Lite bus interface. So every processor core has a bus interface to interact with peripherals. So the MIPS microactive comes with the AHB Lite bus. It's very simple. If you imagine any bus interface with a read bus, write bus, some clocks, that's AHB Lite. It's one of the most simplest ones in the use, but it's a standard. So any peripheral that conforms to AHB Lite bus standard can be connected to the MIPS core. And we have some peripherals within MIPSfpga package itself as well. Okay. So just to recap again, 5-stage pipeline, MMU, we have performance counters. There's no DSP, we keep getting asked about that. Bus, and core extend, yeah, so you can define your own instructions to add using the core extend feature in MIPSfpga. Okay, so now we're gonna go into how the Verilog module is structured and some of the surrounding interfaces. So at the first hour and a half might look like that we're not going inside the MIPS core. That's on purpose, because we want to know how the interfaces work, how to wire it up, how to bring it up, and then part 2, 3, 4 will go really in depth into the core and how it works. Okay, so initially we'll just like keep circling around the MIPS core and see how the rest of the layout is structured. Okay, so we have 1 kilobytes of boot code RAM and 256 kilobytes. This is SRAM on the FPGA. This is the physical. I'll go with the physical memory layout after a while. Yeah. So in terms of memory, it's a 32-bit microprocessor. So 000, the address here. There's 256 kilobytes of RAM from here. There's 1 kilobyte of reset or boot RAM that we call at 1FC0000. This is MIPS special. Whenever a processor comes out of reset, it fetches an instruction from here always. So there's always a scratch RAM here. It can be just one instruction to jump elsewhere if the memory is somewhere else. But this is like, people generally put the very early boot code, the boot ROM and stuff like. In MIPSfpga, this is a scratch RAM. We can load stuff from the bus blaster and work like that. Okay. So 1 kilobyte at the code startup. This can be used for code and for data. So if there's a lot of data, you can use 256 kilobytes just for data and just 1 kilobyte for program memory, or you can use half of it. It depends on how your code is structured and how you want to use the memory. But we're looking at the physical hardware platform at the moment. So coming back to the system diagram. So We have the SI clock in, it's 50 megahertz for this instance. We have the reset, asynchronous reset. We have EJ tag wires interface. This is brought out on the header. I'll go over the physical as to where everything's wired out physically on the platform, but in terms of Verilog, we have signals for EJ tag. We have signals for the AHB Lite interface, and then we have some AHB Lite peripherals already, which is the RAM, the 1 kilobyte, 256 kilobyte RAM I mentioned. We have a GPIO AHB Lite peripheral, and we have others that the whole system gets more complicated as we add more functionality as the labs go on. But for now, we have LEDs, switches go to the FPGA board, EJ tag comes out, goes to the bus blaster, clock from a PLL, reset wire from a push button, fundamentally. Okay. So some more in-depth slides. The reset, it resets the processor. It's wired to the CPU reset button on your boards. The clock in, system clock, 50 megahertz. It's derived from the onboard, like the Nexus 4 DDR board has a 100 megahertz crystal, and we use a PLL to just make it 50 megahertz. SI is a MIPS prefix for system interface. When we give customers a core, we tell them this is a list of signals that you need to wire up, and each signal is then described. So SI ones we use for system interface. The AHB bus itself, the signals are prefixed with H for the bus. Simple 32-bit address, 32-bit data, write data, read data, write signal, and a clock. As I mentioned, it doesn't have any complex features like error. Well, it does, but in terms of our use case, we just use address, read, write, buses, and the write enable and clock. So it's a simple bus which works well for teaching students. The signals that are connected to the board's LEDs, it's prefixed with IO, IO underscore LEDR, the red one, IO underscore switch, 16 LEDs, 16 switches, IO underscore push button. There are 5 push buttons on the board, so these are wired out onto the board. Okay. So yes, EJ tag, as I mentioned, it's the signal names are parallel with the JTAG standard interface. We call it EJ tag for subtle reasons. There's not that much different in terms of our use at the moment. So yeah, the signals are prefixed with EJ, test data in, test data out, test mode select, test clock. You can use it to teach EJ tag if you want. That's a whole separate category. What we use, we just basically use JTAG instead of teaching about JTAG much. So this is the board. I can, well, it should be fine, yeah. So you have, each of you has your own board, some of you are sharing. There's the USB programming port. This is how we load the bit stream on the left side. There's a power switch on the top left. The mode jumper, it should be in this setting on all your boards, hopefully. It's on the left jumper when you have the serial connector. Should be in this setting already, but sometimes they fiddle around with it. As I mentioned, the SI underscore reset signal is wired into the red push button. It already says CPU underscore reset. It's labeled on the board. There are 5 push buttons here. It's in the game format with one up, down, left, right, and center button. The EJ tag, so the Digilent calls them P-mod connectors. There are 6 P-mod connectors on the Nexus 4 DDR board, 6 or 5? Yep, 5. Okay, so on the bottom right one, that's where the EJ tag signals are wired out onto the FPGA. And then there's like 16 LEDs on the bottom, there's 16 switches on the bottom. These are wired to the IO underscore LED signals, IO underscore switch signals. Okay, so yeah. Now, memory mapped IO. So how do we send, okay, we want to light up these 8 LEDs and not these 8 LEDs. So how do you map them from software? How do you write it? In hardware, it's easy. You just make the signal high, it works. So using soft processors, we use memory mapped I/O. So basically, the MIPS core writes a register in memory, and the register is basically wired to the I/O itself. That's how we call it memory mapped I/O. So this is the virtual address we picked, the physical address. These addresses, there's basically one register in hardware. The register can be read and written from the MIPS core, and the register's output signals are also connected to the LED. Okay, so from the MIPS core in software, we do a load instruction, a store instruction. We store 0xFFFF into this memory location. The same memory location is just wired out onto the LEDs. Similarly for switches, this memory location is a register. Okay, we do a load word, a 0x load word, all of it, and then we read what's the switch, is it high or low in that. So that's how we use software to read and write from peripherals. It's all memory mapped I/O. Okay, similar for push buttons, it's this register. Okay, so if we write to this address, it will write to the LEDs. If you read from this address, it will read value. Once you start using it, it will get clearer over time. Memory mapped I/O is basically how all SoCs work and interact with hardware peripherals. Okay. So one thing, if you note, the addresses are in the unpopulated memory map. So we have a 32-bit address map, 0x000, 256 kilobytes of scratch RAM. It's up to this address. We have 1 kilobyte here, located here, 1FC00 here. The addresses in the middle, they're all empty. So if you read and write from these addresses, if there's nothing, it should cause an address exception for MIPS. This is what we call an I/O hole in terminology in the industry. So this gap in the memory map is generally used by input-output peripherals in memory mapped I/O. Okay, so we use, there's no physical memory at this address location. So if you want to add your own peripheral, just find out where there's a gap in the memory map, add a few registers there, wire it on the AHB light bus, and once you read write to those registers, it should communicate with your peripheral. Okay. So yeah, this goes a bit through the same with a bit of assembly. So if you do an add in upper immediate to $7, that's one of our general purpose registers with 0x543. It will put 0x543 in $7. Then you do a load upper immediate. This is 0xBF80. This is the location, the virtual address location in $5 register. The store word opcode basically takes $7, what was in $7, and stores it in the location pointed, stored in $5 at the 0th offset. There are labs that go through a bit of assembly if it's transparent at the moment, but it's basically store 0x543 in a register, store the location in a second register, BF800, and then the store word opcode takes the data in one register, location in another register, and stores it in that register. Then after a couple of cycles, the LEDs will light up. The 0x453, those LEDs which are high will light up. Similar for read, we have an address location that we want to read from, BF800. It's the same base, but the offset is 4. Okay, so in the load word instruction, we use the same $5 BF80, but the offset part is 4. So it's the way the instructions are laid out. You try to use the same base address and provide an offset. It's simpler. Instead of storing 32 bits, you store just the 16 bits, and you store the rest as the offset part in the opcode. That's how it works. Okay. So some more C code and MIPS assembly code, but let me just check 1 second, sorry. Yeah, it should be good. Okay, so we'll go over this in a while. It's basically a short loop which writes in memory. These are the LEDs, and the LEDs increment. So it's a while loop. The destination is BF80000. You just write value the same in destination. The value is 1 at start. The value increments, loop again. write the next value, loop increments, write the next value. In parallel, you have the assembly code. You store BF800 in $8. You add 1, and then this one is a loop which basically stores it and keeps incrementing, stores stores the value in the destination address $8. Okay. Okay. So there are many ways to run programs on the MIPSfpga platform. Each way is kind of tailored for different labs and environments. Not all labs can go and buy everything, all the hardware. Some have different FPGA kits. Some want to run simulation only. So you can use Model Sim or XSim Vivado. Okay, so it's well documented in the teaching packages. On the hardware platforms, you can, while compiling your bit stream, splice the program memory in this, pre-initialize your scratch RAM, pre-initialize your program memory, or at runtime using the JTAG interface, you can just load code onto the scratch RAM. The third option here, you can use the UART. So the UART is a simple TXRX pair. We have a Verilog module that takes data from TXRX and puts it in the scratch memory. Okay, so you don't need a bus blaster if you just want to load code. You can load through the UART, but you can't debug through the UART port. It doesn't stop the code. It doesn't use the JTAG interface. It basically is a back channel into the memory system itself. Okay. In this workshop, we have bus blasters. You all have the red board PCB. So we're going to use the JTAG interface. But all of these ways are documented in the teaching package. So if you want to just simulation, you can do it. If you want to do synthesis or UART, you can do this. In the workshop, we're going to use the JTAG interface. Okay, so this is how the bus blaster is wired to the Nexus 4 DDR board. Okay, 1 second, I think we should move to Vivado. Yeah, Vivado now. Okay, so yeah, we're gonna start a hands-on exercise in a while. We're gonna what we'll do is basically load a pre-prepared MIPSfpga bit stream with all the signals that I described. And we're gonna see if all the laptops are functioning so that the exercises later on will be easy. I'll leave this slide for a while, and we can all wire up our boards, and I'll walk around. Let's just walk around and wire all these boards. We're gonna now open Vivado and load a bit stream. I'll show it as I do it, and you guys can follow. Let me just see here. Yeah, that's this one. Okay, so let's open another Vivado. So open Vivado 2016.2.
Why is it crucial that it's 2016.2?
So it is Verilog, and you can move it around. It's just the subtle things that break, and the screenshot is one way in documentation. If something moves a bit, it's not a requirement as such, but the teaching package, all the documentation, all the screenshots, we know it works, and this is what we test with. But you can move forward, but don't expect too much support if something breaks afterwards, just with peripheral changes or something like that. So once you have Vivado open, click in here, open Hardware Manager. Okay, so this screen should show up. All right, everyone. So at this top header here, up at the top of the green bar, it says Open Target. So click it once, and it should have dropped down to an Auto Connect icon. So you should be able to see the banner at the top. Click Open Target once, and then you should click Auto Connect. Okay. So now we should, if everything's okay, we should see the FPGA here. Xilinx TCF DigiLearn XC7A100T. We should see the FPGA, most of you, okay? So then there, in the banner above, it says Program Device, okay? So we click Program Device, we click the FPGA part number, and then we see this screen pop up open, where it asks for the bitstream file and the debug probes file. I'm not using the debug probes file at the moment, the bitstream file, okay? So when we handed the workshop materials, navigate to that folder. you should have. So for in my case, I have it on my desktop in FPL 2017 MIPSfpga underscore workshop. Then in that we have labs. In labs, it's part 1 and introduction. Lab 1 Vivado and the bit file here. So I'll show the whole path. Oops, here. Okay, so it's labs, part 1 intro, lab 1 Vivado, mfp underscore nexus 4 ddr dot bit. So it should be wherever you copied your MIPSfpga workshop folder from the flash drive. Okay, and then we click program. So this flashes the FPGA. So this is the FPGA on my board. Your layout should look something like this. We have the bus blaster, we have this gray cable, we have the green PCB connection board, and then we connect to this corner board here, and it's powered up. So after programming, you have to press the reset button once to reset the core, and then you should start seeing LEDs increment here. Okay, so this is just a program which is in the program memory itself, in the bit stream itself. So remember I mentioned a while ago that you can splice code into the bit stream itself. So within the RTL we just wrote a short loop which basically loops through LEDs. So I'm going to walk around and see if everybody's on the same page here. Alright, so most of you have Vivado working, we've loaded the bit stream. The next part we're going to look at how we load program code from the bus blaster. Okay, we're going to open command prompt and we're going to load it. Alright, so open a command prompt window, the Windows key and then CMD. Okay, you should see this black screen. Can everybody read somewhat? It's as big as I could get in the text editor. Okay, so navigate using CD, change directory, to where you copied the workshop folder. CD FPL for my case. In my case, it's on desktop FPL 2017 MIPSfpga underscore workshop. Okay, so then I have the labs folder. Then I have part 1 intro, part 2 IO. But I want to go into, so we provide a script. It's load MIPSfpga script, and it tries to open the bus blaster and tries to load the code and make it a bit easy to use. So we go into the scripts folder, okay, and here we have the load MIPSfpga.bat file, okay. So as it gave an error at the moment, it says you must enter the directory where your program file is. Okay, so for example, load MIPSfpga /Xilinx labs, something like that. So we're gonna find the path of our example. Let's see, where is it? FPL workshop labs part 1 introduction. We are in part 1, but this time lab number 2 Vivado, lab number 2 underscore C. So we load a C program code. We want to use the read switches. So we want to read from the switches and blink LEDs according to the switches. Okay. So here we'll look at the source code after a while. It's okay. But at the moment we want to see if all the bus blaster and load script and everything's working. Okay. So once we have the read switches path, click here at the top and copy the whole path. Okay. Click, copy the whole path. Now on my command prompt window, I do load MIPSfpga.bat. And then I right click to enter the whole path. I'll move this up if you can see it. Now can you see it better?
Can you make it bigger?
It is as big as I could. I tried, I think. Yeah, it's at the maximum font size. Yeah. Sorry. I'll come and share it. It's basically the MIPSfpga load MIPSfpga bat file in the scripts folder, and the rest of the path is C:, users, my name Zubair Kakakil, desktop, FPL 2017, MIPSfpga workshop, labs, part 1 intro, lab 2 underscore C, then read switches. So now it should open a couple of windows. One of them is the OpenOCD debugger window. The other is a GDB debugger window. but it should have loaded the code onto the Nexus 4 DDR. I'll look at the webcam and see if it's working. We'll flick a switch. Yeah, this time the LEDs are not incrementing, but if your code has loaded successfully, it should look something like, if you flick a switch, that LED should blink. This is a different code than the one that was in the bit stream itself. So I'm going to go around and just go through it. I'll see if I can. Right, is the okay? So this is what I typed. Okay, I'll leave this. No, okay. Yeah. Okay, I'll do it on the screen and you can follow me. The reason this happens is the USB chip on the Digilent board and the bus blaster, they conflict in part numbers. So we kind of have, it's well documented and it happens, it's okay. Go to program files, see program files, imagination technologies, and then there's OpenOCD. Okay, so in the OpenOCD folder, there's this utility called Zadig, Z-A-D-I-G. Oh, it's not showing me.
Yeah,
it's
options.
Okay.
List.
So open Zadig and we'll come and handle the rest. We have at least one working system on each desk. I'd like to request you to share. I'll take a look at some of the non-working ones in the coffee break. We have about 15 minutes before the coffee break. So I wanted to cover lab 10 and interrupts before we break. Is that all right? Okay, thank you. So we've loaded the bit stream and we have loaded some program code through the bus blaster. So gonna change and okay. Slides part 2 IO. Okay. All right. So yeah, peripherals. The MIPS core interacts with peripherals using the AHB bus interface. Mentioned the clock, write signal, address, data bus, the read write. So this is the MIPS processor, and on this bus you have the address decoder, you have RAM, GPIO, extra peripherals. So they are all connected to the bus line, and it depends on the write signal and the select lines as to which peripheral is getting the data. Okay, that's how it works. So we had a few labs. Okay, want to focus on the interrupts one. So interrupts, the MIPS core at the moment when we are looking at switches and blinking them, it's just looping while one loop and just looping through the signals. But we don't want that. We want to press a button, and the push button should actually interrupt the processor core, and then it should execute the interrupt service routine, and then go back into a sleep kind of state. This is what happens in devices. They basically only function on interrupts, and on the other time they try to sleep to reduce power consumption as much as possible, or service other tasks like that. Okay, so lab 10 interrupts. The goal is to demonstrate hardware interrupts on MIPSfpga. So the first step, we need to tie the hardware interrupt signals themselves. At the moment we didn't wire the signals from the switches to the interrupt lines. So in MIPSfpga, we have the SI system interface interrupt signals. There are 8 interrupts. Now in this bit stream, they're also wired to the push buttons. Button right, SINT 0, button center, SINT 1, button left, SINT 2, button down, SINT 3. So there are 4 interrupts, and they're wired to the push buttons. But we haven't loaded any program code. The bit stream part is fine. We haven't loaded any program code to utilize interrupts or have an interrupt service routine. At the moment, it's just a simple while loop. So the way it's done in hardware, it's a hash if define, and if MFP underscore interrupts is defined in Verilog, it does this. If it's not defined, it just wires them down to 0 for looping. it's okay for now. We'll look at the program. Sorry. Oops. Keep mixing up. Yeah, the interrupt handler. Okay. So the interrupt service routine in program code in C. I know it's a bit tricky to think Verilog and then step right into C and keep juggling back and forth. This is C code, this is program code. It's the interrupt service routine. Okay, so when the interrupt is fired, program execution comes here. It checks the cause of interrupt. First it reads the coprocessor 0 cause register, stores it here in a variable cause. It checks the cause register as to why the cause. So in the cause register, if you open the data sheet, it checks if bit 0 is high, this is the cause of the interrupt. If bit 1 is high, this is the cause of the interrupt. If bit 2 is high, this is the cause of the interrupt. So it checks the cause register. If it's not one of the ones that we have assigned, it stops and loops, etc. This is to capture any unwanted interrupts that happen in the system. The code that we are interested at the moment, if the cause is h int 0, okay, display FFFF on n. Store FFFF in the variable n. We'll see what n happens later. If the cause register and h int 1, so it ANDs a defined value for interrupt, the bit mask for interrupt 1 with the cause register. If this is true, it stores 0 in n. Basically, n is then later on looped and mapped onto the LEDs. So that's what we do. The variable n, we should have just named it LEDs. But yeah, if the cause register and are defined for interrupt 2, the mask, we check only that bit. They're not defined, but it should be something like bit 7 or 8. It depends on the data sheet. If this mask is true, store here. Similarly, if this mask is true, store here. Okay, yeah, so that's what it does. MFP underscore LEDs is another variable. You store the value of n here. So this happens in the interrupt service routine. This code only runs when you press the push button and you've loaded the program code. And then when you press the push button, it happens once. Okay, so now we look at the main function. Okay, so this is the, when you load the, yeah?
Where do you clear the interrupts? I missed that.
For this mode, it should, once it's red, it clears it.
Once it's
yes. So you're right. It depends on the data sheet and the mode. In some cases, you have to store 0 to clear the interrupt. If I remember correctly, once you read it, that in the basic mode, it clears it on the first read, because then it assumes the software has handled or read it. Yeah, usually in the interrupt service routine, no other interrupt can interrupt the interrupt service routine. You understand what I said? You can't interrupt the interrupt service routine itself.
You still can press 2 buttons and the refresh will miss one.
So it will come back and run it for that.
It clears one specific interrupt, it clears all that's
That's a good one.
all that's active.
Yeah. For in this routine, it should. You're right. Yeah, if you press 2 simultaneously, you're right.
Okay.
Well spotted. Well spotted. Yeah. Okay. For the main function, when you load the program code, it enters here the main. It clears boot interrupt vector bit in coprocessor 0 status register. This is part of the preparation for enabling interrupts, and it sets the master interrupt enable bit as well as individual interrupt enable bits in coprocessor 0 status register. So this is the right. So interrupt enable bit is enabled, or hint 0, we looked at it a while ago. This one's enabled, hint 1 is enabled, hint 2 is enabled, hint 3 is enabled, hint 4 is enabled. So these 5 interrupts are enabled along with the global interrupt enable register. Okay. Now the register has been configured, but until you execute the EI instruction, interrupts aren't enabled. So the reason this happens is, for example, if you have 2 cores, you want to run EI and then you want to prep as much as you want for the IO interrupt handlers. You want to prep all the status registers. You don't want the moment this happens for an interrupt to stop until you've done all your preparation. So you want to do all your preparation and then run assembly EI instruction, enable interrupts, and at this point all the configuration will, the next few cycles later, it will all start working. Okay. This loop is basically just a simple while loop. It disables interrupts. The reason disable is here is to show how to disable interrupt. It's not a part of the program. It's more of a, this is how interrupts are disabled, this is how interrupts are enabled, and the MFP LEDs, and it's just a while loop here. Okay. So this is located in, yeah, we can go with the hands-on. It's located here. MIPSfpga labs, part 2. You open the workshop folder. This path is for the one you download from the. In part 2 IO, there's lab 10 interrupts and interrupt program. So you can use the same load MIPSfpga bat, just change the path to interrupts program, and you're free to open the source code, the main.c file, and then we'll see. Okay, so I'll run around, what's the time? I think it's about to be coffee break.